Okay, good morning. Sorry, I actually missed last Tuesday's class. I asked one PhD student, Xiang Ren, replace me to give the lecture. Hopefully you learned something still very well. I actually just came back this morning because I got last night, the flight, they actually got missed the connection. So we have to drove back until this morning. I actually drove back after midnight, came back. But it should be fine. One thing I should announce is we do give you a sample final exam. That's some previous years. You probably can see that's some years. I did not say what year it is. But I should say because this is a few years ago, the current one will be rather different. Okay? You cannot just rely on what exactly question we are asking. You have to really see just as the styles of the exam, okay, the final exam. The final exam, we will cover the data pre-processing. You can see that we also will cover data warehouse, OLAP, data queue. We will cover pattern discovery. And then we will cover classification. Of course, classification is a little longer chapter because we have 2 chapters on classification. Then we have 1 chapter on clustering. Okay? So that's a distribution you probably can see. Any chapter, we go down to the detail, give you many questions. The general philosophy is you have to master many of them. I also said I do not expect you to remember everything. So the same thing as many years, we basically say you have 2 sheet reference. That means you can keep 1 sheet in your midterm if you don't want to throw it away. Then you can get 1 more after midterm, you can get another sheet. That's why I say you need to consider 2 sheets of reference. You can put formulas, definition, or important things, whatever you like. Okay? Printed in whatever font. Okay? Make sure you bring it, because in the final exam, some people say, I just cannot remember so many things clearly or in some precise term. You have those references, it may help you. Okay? So these are important things. On the other hand, we will not ask you to put the formulas or definitions right on in the exam sheet, because usually we test you how you understand it, how do you master those things to do some further work. Okay? So that means give you the sheet will help you, but on the other hand, we give you the question somewhat more challenging. Okay? So you should treat this seriously. Okay? Another thing you probably saw in Piazza this morning, the TA already announced, we do give you an alternative exam if you just cannot make the regular exam time. Okay? The regular exam time is on December 15th, I believe it's 7 to 10 p.m. The concrete location, concrete distribution, we will work it out because I have to discuss with the university to make sure we don't have too many sites, because sometimes they give us 3 or 4 different test sites. They are very far away. One is in like a soybean center. The other one is here. You have to drive cars, across those different centers. We try to consolidate to have less centers, not too far away, within a walking distance. Okay. So you watch Piazza about December 15th, exactly how to locate, how to see on different centers. Okay. I assume it should not be too complicated, but you need to watch it. Okay. Any other questions regarding to the final exam or final work, including the assignments? Any questions you probably want to ask, because I probably have to announce the next Tuesday, the very last lecture, Xiang will still replacing me, because I'm giving a keynote speech in IEEE Big Data, which is in Washington, D.C. So I will be in Washington, D.C. next Tuesday. So I try my best not to miss many classes. But this one, I already negotiated with them. They said, oh, the other day actually is Mike Stonebreaker's talk. So you are treating almost like a Turing Award to the winner. I said, I'm not. But they basically say it's a big honor to give a talk, so this one lecture probably is worth it. But on the other hand, I also said this cluster analysis is in Coursera course. If some way you can watch the video, then you also can see the whole story. So our whole slides almost form exactly the whole Coursera video for cluster analysis. You watch it, you should learn quite a lot. Any other questions related to, yes? The next lecture, the question is whether it will be a review session or it will be still new class materials. It will be new class materials. It will be not a review session. Okay? Because the review, in principle, you can do it by yourselves. Okay? If you have particular questions, we will set up specific office hours, both for me and for TAs, especially the last 2 or 3 days, you got to panic, you still have problems. Even the very last day, December 15th, I will open some additional office hours. So for any review questions, if you do not understand, you can post in Piazza, or you can come to my office or TA's office. Okay? But we do not spend time on providing a specific review session. Okay? Any other questions? Yeah, the final grading, I should still say, is final grading is curved grading. Curved grading means if you find the question is tough, it could be tough to the whole class. You should not worry too much. On the other hand, if the question is easy, it will be easy to the whole class. You still have to do it really well. Okay. I probably should say the final exam question, you look at it, at least the time-wise, it will be easier than midterm. Because midterm, you have to handle everything in 90 minutes. Now you get 180 minutes. I will not give double questions. You probably can see. I still give like 10 big questions. The midterm has 10 big questions as well. So time-wise, you definitely have more time to think about it and write it. Hopefully, the final exam, you'll get a higher score. Okay, so if there's no questions, I will keep, lecturing. Then you get any problem, you can raise it in Piazza or in some other places. Okay. So I think Xiang actually told me he basically got into something quite close to Birch. Okay, that means get into hierarchical clustering. I probably be from the hierarchical clustering, I give you a very quick review, then I'll touch to the new materials. Okay. The hierarchical clustering general philosophy is we want to work either top-down or bottom-up to construct the clusters in a hierarchical way. That means in the things more like a tree structure. If we go from bottom up, most people actually in statistics community call this one is agglomerative clustering. Okay. So the agglomerative means you start from every point, every object is one cluster. Then you try to see who are closer. You try to merge them. By merging, of course, there are some standard how to merge them. By merging progressively, you actually get it less and less clusters, but you merge many things into different groups. And finally, you merge everything into one. Okay. That's the clustering method we call agglomerative. Then you can go in reverse. In computer science, you say top-down. In statistics, people call this is divisive. Okay? Divisive means you start from all the objects in one big cluster. Then you see where you can chop them. Where's the biggest one you can cut and split them into two clusters. Okay? You split them in a recursive way. Finally, you can split every object into a single cluster. So that process, hierarchical clustering process, called divisive. Okay? So if you look at many research literatures, they actually draw this one into a special figure people call dendrogram. Dendrogram, you probably can see, you can merge things into bigger one, and you merge to the end, you get a single cluster. Or you divide them, partition them into 2, into 3, into 4, so you can go down. So either way, you construct the cluster, the hierarchical cluster, from a dendrogram. Okay. Then the typical method is if you do agglomerative, there's one specific algorithm called Agnes. It's agglomerative nesting method, published in 1990 in a book by Kaufman and Russo. And what they do is they use single link as a way. Single link basically say within this two sides, you try to find what is the you will think what these two clusters, what is shortest thing. Those are single link. Okay. And actually, there are many other ways to link them. You can have complete link, average link, centroid link. Those links we are going to discuss immediately how to evaluate based on these different distance measures, try to compute them. Okay. The single link, you can think is the nearest neighbor or single line. That means you got these two clusters. Their cluster distance. That means you got two clusters. The distance between these two clusters are the nearest 2 points. I mean, the points in A, points in B. The nearest 2 points is the single link. Then the complete link means the farthest points, the most remote points. Okay, these two, you link them together. That's a complete link. Okay. And then quite popularly, we also use average link and centroid link. Average link means you try to compute, you compute all the links. You finally average them. This, of course, is very expensive to compute. That means you average all the distances between one element in cluster A, their distance to every object in cluster B. Okay. Then you get every object in cluster A going to measure to every object in cluster B. All these distances, you average them. Okay, suppose you think here you get 10, here you get 10, 10 times 10, you get 100. Then you basically compute this 100 distance. You average them, that's average link. Of course, this computation is very expensive, but there are algorithms, they do this. There are many algorithms, they actually use average link. Another popularly used method called centroid link. This is also popularly used. Centroid means for each cluster, you calculate your respective centroid. Okay. Then you link them together. You say that distance between these two centroids are the centroid link. Okay. That's a different clustering algorithm. They may use different measures, different links. Another one called group average agglomerative clustering. Group average essentially is you partition them into different groups. You look at the groups, they are centroid link. Okay. And there are different other methods. But most popular used are the shortest one called single link, or the maximum one called complete link. Then you get an average link and a centroid link. Those are the most popular used methods. For the same reason, you can do the divisive clustering. Divisive clustering means top-down. Okay, you start from one cluster, you try to chop them. And there are different ways to measure them. You still can use single link, complete link, everything, or central link. You use different linking methods to evaluate them. And there are many, many algorithms using different methods. I think the last lecture already give you this. But people say the hierarchical clustering, of course, is popularly used. But the problem is once you split or merge, the decision is almost like a final. Then you cannot adjust it. Remember the k-means, you can adjust it. You say, I first partition this way. Okay. Then I found it may not be so good. I trade. I say, I change my center, then I grab new objects. I throw away the far away objects to the other one. So you can regret. You can change your original partition. Okay. But the hierarchical clustering, the problem is you make decision in a careful way. You evaluate the single link or complete link. You evaluate the careful way. You try to chop it, or you try to merge them. Okay. Once you chop it, the decision is final. You do it recursively. You just cannot regret. It's more like you play chess. Once you place the one and say, people say no retreat. Okay. You cannot regret, even you did a wrong one. Okay. That's the same thing. The hierarchical, basically, you place your bet, then that's it. Okay, you cut it, you do the recursive. It's efficient to some extent, but it's final. You just cannot regret. But there are newer algorithms that people try to do better in a hierarchical way. The better one, we are going to introduce all the three, but the first one is probably the most interesting one, called Birch. We're going to introduce this algorithm. This Birch algorithm, the general philosophy is hierarchical at the very low end. You do the hierarchical. Once you get into bigger clusters, then you can use any algorithm. They give you complete flexibility. You can use any algorithm you like. Okay. The general philosophy is scalability. What is scalability? Means you got really, really lots of points, lots of data. You think about it in nowadays, you go to web, say, suppose you want to cluster web pages. How many web pages you have? You have tremendous. You have so big data. If you use the previous hierarchical clustering or k-means or any algorithm, you do iterative, thing. It's very costly. You evaluate every object. There are millions of them. Okay. So there must be some, invention to develop a very scalable algorithm. That means no matter how many data you give me, I can do it in a very efficient way. Okay. And this Birch was developed in University of Wisconsin by a PhD student, Tian Zhang. Okay. Actually, her advisor, Raghu Ramakrishnan, actually was a professor in Wisconsin, later lead Yahoo research. I think now is vice president in Microsoft. They three actually work out a multi-phased clustering algorithm. It's very interesting because their major competitor of this scalable clustering algorithm is ours. Professor Riemann Ng and I, we jointly wrote a paper in VRDB 1994. We published in 1994. It's called Clarence. Essentially, it's the algorithm on the k-meter algorithm, but we do random sampling. Okay. Some kind of simulate that meaning doing this random sampling. That means every sample, the next round sample different things. Okay. Then we can make it reasonably high quality, reasonably scalable. But it's still not scalable enough. You give me millions of points doing the sampling. If your sample is too small or too random, you may not always guarantee high quality. They want to count every data, every piece. Okay. So they actually compare with our algorithm to show their method has better quality, better scalability. So what they did is the general philosophy, actually this paper is so interesting in the sense, after 10 years, okay, that's 2006, Sigma conference, which is top database conference, they put this paper as the highest impact paper award for 10 years. That means in 10 years, they found that this paper was cited most frequently for that year's all the papers, and also have the most follow-up to a lot of other pieces of work. So I probably can give you some general philosophy, then you will see this algorithm actually is very nice. The general philosophy is this. You got lots of data. You want to somehow group the data based on their locally, they are very, very tight, very compact. You try to put them together, say this one is a cluster. Okay. But how, the first thing is how to evaluate they are very compact. They give a method called clustering features. The clustering feature, they have 3 ways to judge its compact. One is N, is number of data points. Number of data points means they want this cluster, every cluster is reasonably even. That means the number of points is somehow, for example, you get a, suppose you have 1 million points. You may say at the very beginning, I may have somehow like 10 or 20 things grouped together as one small cluster. So this N should be somehow similar, should be even. Then the second one is a linear sum. Linear sum means if you look at every dimension, okay, you sum them up, they should be rather compact in the sense these objects, they are in the same cluster. Their X value and Y values should be somewhat similar. So you can think about this. This is obvious, right? You don't want to getting one point is in Champaign, the other point, suppose in Washington, D.C. I was there yesterday. Okay, you get these far. You say these are in the same cluster. Obviously, it could be you generate something ridiculous. But if you say, oh, this is Champaign, I want to get one maybe in Bloomington, in Decatur, or in Rantoul, or those similar ones, you put together. They are X, Y value is similar. Okay, so this is a linear sum. The third one is SS, means square sum. Square sum means not only they linearly they are compact, but even you square them, okay, their distance is still. Remember, sometimes you cannot judge what should be the same. You can think you have positive, negative, or something. Once you square them, you say even the squared distance is still compact. Okay, that means you have 3 things you can judge. One is that you can say zero moment is discount. Then you say linear sum is 1 moment, 1 order. Then SS square sum is a second moment. That means you even square them, they are still close. Okay, so you can think about this. You probably can see there are 5 points. Okay, these are 5 points. You linearly sum them together. The X sum them together, Y sum them together, get this value. Okay. Then you can square them. You can say 3 square, 2 square, 4 square. You sum them up, you get this value. And here you get 4 square, 6 square, 5 square. You square them, you put this here. You can see this clustering feature basically say, I want to group something very close to me. Okay. And I have 3 guarantees. Number is close, linear sum is close, square sum is also close. I group them together as one cluster. Okay. So you probably see that's a design is quite reasonable, right? You get this clustering feature. Okay. That means you can think this is a summary of the statistics of a given subcluster. You get a zeros, first and second moments, and you say these subcluster from the statistical point of view, they really glue together. Okay. They are very close. And once you glue them together, how you do the remaining? The data is really big, right? So what they say is they try to measure their centroids, radius, and diameter. Okay. the centroid essentially is you can think it's the center of the cluster. Most people measure centroids use a very simple computation. Is you just get every dimension, you get their average value. That means you map to x dimension, you just for this dimension you get an average, this mean point. You map to y part, you get a y's mean point, then you get centroid xy. Okay, so that's very easy to compute. Even you compute in like a geometric center or something, you compute it's not too far apart. So this is the easiest way. Most people compute this way to get centroid. Okay. Then what is a radius? Radius actually is you see every point in your cluster. This point, you calculate the distance, and you calculate any other points. All these points, you calculate, you get a square them, and you sum them. You calculate their endpoints, you divide by n. Okay. Then you take square root. That's the one we called the radius. Okay. But the diameter actually is, I should say this, okay, I should say it back. You first get centroid. The radius is you take every point, compute their distance with the centroid. Then you get a sum of their square. You divide by n. That's the one you get a radius. But the diameter computation is you get every other point. You ignore the centroid. You just say every point, okay, in your cluster. You try to calculate their distance. Then you calculate the sum of their square distance. You divide by all the possible combination, which is n times n minus 1. That's a radius. The radius is not like you think the radius like you measure a circle. You say radius is the longest one. That's a radius. Actually, in cluster, you have thinking something in the middle. You calculate, you get all their relative distance. You average them. That's a radius. That's a diameter. Okay. So you probably can see the centroid, radius, diameter, the computation. Right. And then this one is probably the most important picture you can get for their idea. Okay. Their idea is this. Okay. You got huge, like millions of points. You want to do hierarchical clustering. How you do it? You do it in a balanced tree way. If you think about it, these people actually start with the relational database people. Database people like the B tree, B plus tree for the relational database indexing. Right? You get a lot of entries, millions of them. You construct a balanced B tree, B plus tree. Okay. So this idea is very much like a balanced B plus tree, but for clustering. What they do is they got many, many points. Their CF vector is similar. Similar means you get similar number of points. You get similar from the linear points, from the linear sum or linear average. And you get a square sum, a square average. You get a zeros, first, second moments. They are very close. Simply say those are the small clusters. They are very close. You say, these CF vector, these small clusters, very close, I put them into the same leaf. Okay, suppose your leaf can hold, say, 6 clusters. Then you pick up the very close 6 clusters, you put them together, you say, this one actually is a bigger cluster. Then you put as one leaf. You can see each CF is a small cluster. Then you put those small clusters, they are very close. You put them together as another bigger cluster. Then you do this one recursively, construct the whole tree in a balanced way. Essentially, it's a B plus tree algorithm. Okay. What's the idea? Okay, their idea later, they generate one in computer magazine or somewhere. They just explain their idea. The idea generally, you can think in this way. They write it in a very vivid way. Say, you go to the beach. people ask you to cluster the sand of the beach into several clusters. Okay? And there's so too much sand, right? Too many grain sands, millions of them. How do you do clustering? You can thinking the sand is just too many. I cannot count them. It's so inefficient to calculate every grain of sand. What they do is, what about we first do local clustering? We cluster sand into tennis ball. Okay, that means you will think the sand, actually every piece of sand, they are very close, they form a tennis ball. But you say, oh, once I got a tennis ball, this beach is so big. There are millions of tennis balls. It's still very big, right? So what about I took those very close tennis balls, I think they are actually the beach ball. Okay. Then you get much less number of beach ball you have to consider. Of course, this beach ball can even roll up into a very big ball. Okay. Then you cluster in those big ball. You don't have that many clusters. You probably can use a nice clustering algorithm to do it. And no matter what clustering algorithm you want to do, you don't want to go down to every grain and sand to break them up because they're already very close. They tie together. You think it's a nice cluster. You get those big ball. You say, based on this big ball, I chop this into different clusters. The accuracy, the desired cluster will not change. That's their idea. Then you can make it really efficient. So now that's their CF tree structure in their algorithm. Birch essentially is multi-layered B plus tree. Okay. But they do not call this B plus tree because they do not store indexing structure. They call this one is a birch tree. Okay. The birch tree essentially is a balanced tree. The lowest part is the lowest granularity of this tiny, tiny cluster. Okay. But those subcluster grouped together into a leaf, the leaf grouped together into some non-leaf nodes. The non-leaf nodes may have multi-layers. But they said, also they give a very good point, is they say they do not suggest you go all the way, say that's exactly the cluster you want. They say you get into certain layer, you can apply any clustering algorithm on that layer if you think that layer is desirable. For example, if that layer contains the non-leaf nodes, suppose 100, okay? Then you say everything is like a big ball. You totally have 100 balls. Then you can do clustering using any algorithm. You can use, actually they use our algorithm, Clarence, the K-meter-based algorithm, to do that. So they show their results is more scalable, and the results is better than ours because we are using sampling. They count every point. So that means they can kick in any algorithm. They are not binding to the hierarchical. But the hierarchical, at the lowest level, they did use hierarchical. So it's a very nice algorithm. And this algorithm has a very high impact. People doing very many data points to do clustering, many people using this algorithm. Yes. Yeah, the question is, this one essentially is bottom-up hierarchical clustering, right? Bottom-up, when you want to stop. Okay. They basically have two stages. One stage is this purely, they call micro-clustering. That means you start from the tiny nodes, you do the micro-clustering, you get into a certain level. But this level, they did not say firm, say whether it should only have 50 bigger microclusters, or you should have 500. Okay. That's complete depend on your own application, which is right. You think you get millions of points. Maybe you think I finally get 500 points, 500 small clusters will be good enough for me to work. The other people may say 500 is still too big. I may want to get 50 or 100. So it really depends on your application. You can say at which level you want to start working on some other algorithm. There's no specification. This is just principle. And they did a lot of performance study shows, like they show some image they want to do clustering. They show this method to do clustering, they get a very nice image. And of course, there are many other applications. We actually also use this one to do stream clustering. Stream clustering means if the data come in like water, like a stream, and you get a huge amount of data, how do you do it? Because you have to forget those streams data. So what we did is we keep dynamically generate this microcluster at a certain level. Okay? And we just keep the statistics of it at a certain level. And we show actually, no matter what kind of data, you have very limited memory, main memory. You have a very fast data stream with a very big amount of data. And if you use this idea, you actually can keep the most essential statistics intact. And you can do very high quality clustering based on the data. Of course, we even determine the timestamps. That means you even can compare how the cluster evolving at a certain level. So that algorithm itself has been cited very popularly, but it's based on this idea. And then there are 10 years award paper. They actually show many follow-up work. One work is our work on clustering, and in the stream clustering idea, how to use this philosophy, and it's very effective. Actually, that work is our group working together with IBM Research. IBM actually later, they developed an engine, a big system called Stream. Okay? Their clustering algorithm is exactly using our algorithm. Okay? That implies this birch idea is very powerful. So this is, you probably I can review this birch. You can see it's multi-phase clustering. Multi-phase means the first phase you do the micro-clustering. The second phase you can kick in any algorithm and do another refined clustering. Okay. You can see the phase one is you scan database to build initial in-main memory CF tree. Essentially, it's a B plus tree. It's a CF is clustering feature tree. Okay. It's a multi-level compression of the data that tries to preserve the inherent clustering structure of the data. So that's the first phase. You get a low level, many levels of trees. Then the second phase is use an arbitrary clustering algorithm. That means you can pick any algorithm you like. You can use arbitrary clustering algorithm to cluster the leaf nodes of the CF tree and a certain level of nodes, non-leaf nodes so this essentially is a multi-level clustering. You do low-level micro-clustering. You can reduce the complexity, increasing the scalability. Then for the high-level macro-clustering, you have enough flexibility. That means you can use any algorithm you like to do the clustering, not necessarily hierarchical one. You can use k-means, k-medots, or any other clustering algorithm you like. So it has a linear scalability. Because the B plus tree, the insert tree is a log. You can insert tree in a logarithmic scale. So the whole cluster algorithm. So that's the general idea. You can see they have a nice design and you get a very good results as well. It's very scalable. So you probably can see this birch is a scalable, flexible clustering method. It has a agglomerative clustering. Essentially, it's a low level doing micro clustering, high level doing macro clustering. And they have a lot of other follow-up clustering methods. That's why they got thousands of citations. Okay. And of course, when the data points come, depends on when they come, what's the order, the tree will be somehow different. Because you think about originally you glue things together already. Then they come a point, you get too many points come almost to the same cluster. They may either absorb them or they split them. It's different if you come earlier or come late. Their aggregation, the result will be different. Okay. So that means it's sensitive to the order, and also you have the leaf node is fixed size. Sometimes you cannot do arbitrary shape at the low level. With the high level, you still can do arbitrary shape. The cluster usually the spherical means it turned to be like a ball, because the hierarchical clustering in most cases you get something very close to a ball. Then people actually think you may want to do clustering. Finally, you may not want to get a strict ball, okay, because the strict ball sometimes cannot reflect the real shape of the cluster. Okay. Then there are people actually thinking about other methods. There's one proposed method is called CURE. It's clustering using representative points. Okay. What are the clustering using representative points? The general philosophy is this. Okay. You can first do some small clustering like this. You can see here you do a lot of small clustering. Then once you do small clustering, you find their centroids, their most representative centroids, like midpoints. You can find those. And then you actually want the midpoints, they are very close. You want to do a little twisting on their midpoints, means you actually you will have a shrinking factor. Those things are closer, you try to shift their midpoints a little to make them even closer. So finally, you will be able to find a cluster which is not in the ball shape, not a round. It's kind of a little arbitrary shape. You still can find it. This algorithm was done by Guha, Rastogi, and Kyosuk Shim. Guha, I think, probably still a professor in UPenn. Okay, at that time, he was a PhD student. These two was in the Bear Lab. Actually, now they all gone. Rastogi is leading Yahoo Lab in India, I think. Kyosuk Shim is a professor in National Seoul University in Korea. Okay. But I actually met them in many conferences. They actually, this algorithm, the general philosophy is you do the small microclustering. You can think it's like a bird. You do small microclustering. But then you do not fully trust those microclustering. You get their center, but then you try to see whether you will be able to find those close to one, and you try to shift to the center of gravity. By shifting this, you will be able to grab those things. For example, like these ones not really look like a round shape, a spherical shape. The reason is once you move your centroid somehow closer, those things will not be split. Because then you find those longer shaped clusters instead of a round shape. That means they have a shrinking factor, then they can actually capture the clusters of arbitrary shapes. Like they give you example like this. Okay. Suppose they generate many, many points in this shape. If you use, suppose you k-means algorithm, what you will get? You will get a cluster like this. You can see it's very ugly because you break those things into many different colored clusters. Like this one. The big ball should be one cluster. Those small ones should have two small separate clusters. By human eye, you can easily see it. But if you use k-means, you say, I want 3 clusters. They will likely give you 3 clusters like this. This is pretty ugly. But by using their algorithm, you can see they can shift to the center, then they can separate this in a nice way. That the color probably can show you the final cluster result is really better. You can see those are different clusters. These are 3 different clusters. So that shows you just strictly based on the radius, the distance, you may not get a very nice cluster. Then in those years, you probably see around 1994 to 1999, there are lots of new algorithms proposed. This one was proposed by University of Minnesota group. Okay. George Karpus is now still a professor. In that time, he was a postdoc, actually, in Minnesota. Vipin Kumar is also a professor. He's a department head, I think. These three, actually, this is not me. This is another Han. He's a PhD student, originated from Korea. Okay. And they work out an algorithm called Chameleon. Okay. Their algorithm is a graph partition-based approach. What they do is they link everything into graphs, then they do graph partition, then they recluster it. Oh, let me show you a picture. Probably that's the best way to describe it. Suppose you get very large data sets here. Then how do you get the clusters? They say those data points always you based on their connectivity. They are very close. You can think they have an edge to connect them. Okay. So you based on their connectivity, you draw graph structures like this. Okay. Then you can use graph partitioning algorithm to partition this into many small clusters. At this point, you don't care how many Ks, what is the K value, and you actually partition much more than the K you need. For example, you say I want to have 3 clusters. You probably partition them into 30 or something based on the graph partition. That means they tightly connected, they are closer together. They are not so tightly connected, you can break them using some kind of partition. You know, of course, there are many graph partitioning methods. If you study networks, you will see there like a min cuts, or there are many different cutting min cuts. You can cut in a minimum number of edges. You can cut it, you can separate them from the other parts of the graph. So you can use a graph partitioning algorithm, partition them into many, many small graphs. We call these small graphs as graphlets. So you can see, you can partition them into graphlets, and then taking every graphlet like a point, you measure their connectivity with the other graphlets. Okay. Then you can merge them back. That merge is a little careful merge. Simply says graphlets itself is like a small cluster. Okay. Then you take those small clusters, they have the weights. Okay. Then you, based on their distance, their connectivity, you merge them back based on the number of clusters you need. Okay. Or based on the graph similarity measure, you can merge them back. You can get final cluster. And what is the standard? You do initial cluster, you do merging. The initial cluster you can just based on the K nearest neighbor. That means you look at your nearest neighbor, you find they're really near, they're close, you partition them. This graph partition is based on K nearest neighbor algorithm. Okay. Then this merge one is evaluated based on relative interconnectivity and relative closeness. Relative interconnectivity means you get internal, they have lots of edges connected them. So you justify based on their connectivity, interconnectivity. The closeness is based on some numerical closeness measure. Okay. Let me just give you, we go back a little, you can see that they have the two measures. In the very beginning, you chop them. That means you use a graph partitioning algorithm, like a k-nearest neighbor partitioning algorithm. You cluster objects into a large number of relatively small subclusters. To that extent, it's kind of a hierarchical cluster. You do agglomerative. You glue them together. Okay? So that's K and k-nearest neighbor glue them together. Once you partition these graphs, you use agglomerative hierarchical clustering algorithm, try to recombine them together. And recombine, you need to judge based on interconnectivity and closeness, these two measures. Let's look at how they define the closeness measure. Okay. The first one is k-nearest neighbor. nearest neighbor is a very popular used algorithm. You can think about it. You may have one nearest neighbor. You may have two nearest neighbors, three nearest neighbor. One nearest neighbor means you just justify who's my closest. Okay. Then you try to build an edge. If it's within certain threshold, you can build an edge. And based on this edge, you can work out these one nearest neighbor. Or you can use two nearest neighbor. Every time you judge who are my two neighbors closest to me. So then you can draw a graph like this. Or you can use three nearest neighbor. Of course, it depends on your real data sets. You may just use one or two or three. But anyway, you use more K to work well. Then, based on this, you actually work out when you want to remerge them, remerge those graphlets, you want to use interconnectivity. One is called internal interconnectivity. Another is relative interconnectivity. These two measures. Okay. The measure essentially is based on the distance on the cluster center. You use those kind of measure to measure it. Okay. And this relative closeness is based on this kind of measure. Essentially, you weight the edges. The edges, you get many points. You weight a little more on the number of clusters there. And you, based on the distance, you can weight it's far away, the distance should be smaller. It's very close, the distance should be bigger. You can, based on these, you can merge those those subclusters. Then you can see the results they show. Okay. Of course, the cluster, the easiest one is to generate many points in different shapes. You will see those clustering algorithms, whether they will get a cluster you really think they should be. You actually can see is those are all the points. The color is the clustering results. That means whether you really can cluster those, for example, you see those different colors. By human eye, you can easily judge the results is very good. The reason is you can see those very good shaped ones, you did not partition them into different ugly ones. Those look like a cluster, they are in a cluster. Remember, those clustering algorithms blind. They do not know. They just go inside based on the number of points, based on their closeness, based on this. They partition them into graphs. You actually can see they use many different algorithms. They show for the same data sets. You can use Birch, you can use many other algorithms to show which algorithm gives you the better result. Okay. They basically show they use their graph partitioning and remerging, get the very best results humans can get. So that's the clustering on very complex objects. So I did not show you the other algorithm. Actually, the other algorithm we compare, they also show the pictures. The other algorithm may not provide as good clusters. So this is the hierarchical clustering algorithm. You can see the strict hierarchy, top-down, bottom-up, we call agglomerative or divisive, may not be very good. The reason is it's too rigid. Once you did it wrong, you just cannot correct it. And then you look at those further developments, like a birch, like a cure, like a chameleon. They do better work. They still use the hierarchical idea, but they are not so strict. They actually use a little more tricks. Like they get into microclusters, and then they can use any other algorithm. Then we will discuss another idea is probabilistic hierarchical clustering. Probabilistic hierarchical clustering is you just assume everything is generated, every point in your real space is generated by some kind of model. Okay, they call it generative model. Okay. And the generation is always based on certain probabilistic functions. Okay. That means you can think those clusters are some human or some process generated. But from the statistician's point of view, these are all generated by some kind of abstract mathematical model. They generate these points. Okay. And why they form a cluster? Just because they generate in a similar function, they generate many, many points. These points have the similar statistic function. That's why they generate as a cluster. Okay, that's basically their philosophy. Then this hierarchical clustering, the probabilistic hierarchical clustering, the general idea is you actually try to find their underneath the probabilistic function, whether you can get this model. And once you can get this model, you probably say that's the model generate the data sets. I have 2 or 3 different things. I generate different things. Okay. So that's the general idea of this generative model. Then what you do is you can think, we first just thinking about a one-dimension point, single-dimension line. And for this one-dimension point, what you can think is every point of the generation is a Gaussian distribution. You can think you got this point. How this point is generated is generated by some kind of Gaussian. Okay. So that means you can use a Gaussian distribution function like this. You can say these points actually generated by this function. Okay. Then you can say for a particular point, the Gaussian distribution generation is a probability distribution. The probability means you get a mu, you get standard deviation. This is mean, this standard deviation. This is the general Gaussian distribution. Okay. And this is based on this Gaussian distribution, what is probability this xi, this particular point will be generated. Of course, you assume you have a function generating, you generate all the points from xy to xn. Then this particular xi, the generated model, should be like this one. You can see this is the whole distribution. This is the probability of a particular point xi generated this way. Then if you think about this m points, whether you generate by this Gaussian distribution, is you think about these m points, there's a likelihood this generative function will generate the whole thing, generate whole m points. Simply says, if you want to compute, you assume these m points were generated by the Gaussian distribution with this particular mu and particular sigma. Then you will say this x, this m points, there's a likelihood using this function you can generate all these m points. Okay. Then how to calculate this likelihood is using this one. Okay, you can see this formula and this one, they are similar. This is a general distribution. This is these m points you judge whether they fit this function well. Okay, then you can see you multiply all these by probability, you will get the likelihood. Okay. Then how do you judge whether it should be a good cluster or not? Is you try to find the mu and the sigma, because you do not know, you just assume there's a mu, there's sigma, generate this. Then you try to find a mu and sigma to get this maximum likelihood. That means they can generate many, many things. You can think a different mu, different sigma, they generate this. You do not know which mu, which sigma generate this m points. But what you finally compute will be the maximum likelihood. That means you try different mu, different x, different mu, different sigma. You try to find the mu and sigma which give you the maximum likelihood. That means most likely generate these endpoints. Then you find the cluster. Essentially, the cluster is, you really can say these endpoints actually will generate by this one. So that's the generative model. And using this generative model, you can calculate all these distributions. Then you will be able to find different clusters, because you can see this one is generated by 1 mu 1, sigma 1. Okay. This one could be generated by mu 2, sigma 2. Okay. You can think about it. This could be the generative function generate this mu 1 as two different generative parameters. They generate these two clusters. Okay. That means try to do this is try to derive these likelihood. Okay. How to derive this likelihood? Okay. There are several ways to derive likelihood. Actually, in this lecture, I'm not going to discuss this because it's a longer story. The most popular used is called the EM algorithm, expectation maximization algorithm. But that's a little longer story. I actually use another, in the Coursera, I could use another course, just describe this EM algorithm. In this lecture, because we have limited time, I will not cover EM. You just know there's some kind of a computation magic. Okay? Essentially, it's iteratively refined computation. You will be able to derive this correct mu and sigma to do the right clustering in the probabilistic statistics. To a certain extent, what you can think is it's somewhat like a k-means. Okay? But the major difference is this one is a soft k-means. K-means you do this hard partition. You say this belongs to cluster A, it will not belong to cluster B. Okay? And this distribution one is soft in the sense you get any point. You say, belong to this distribution, there's a certain probability. Belong to the other distribution, you have a higher probability. That likely this one have a higher probability belong to this cluster rather than the other cluster. But you still have a small probability belong to the other cluster. So everything is soft. They do soft clustering. That essentially is EM algorithm. So using this probabilistic model, you can do hierarchical clustering. The hierarchical clustering, the general philosophy is you calculate the maximum likelihood, then you try to partition this based on these maximum likelihood. The general philosophy is this. Okay. You calculate those probability, calculate this maximum likelihood. In principle, you can calculate the cluster. You get M clusters. You can calculate the likelihood like this. Okay. Then you can say, now I don't want to think this one is one cluster. I want to partition them into, say, two clusters. Like this one is one cluster, this one is another cluster. The partition one, in principle, should improve your maximum likelihood. That simply says, if you can partition this, you find if your original cluster in this way, your partition the cluster this way, your quality function actually improves. That means you calculate this maximum likelihood, it improved. That means originally you, based on everything is in one cluster, you calculate this maximum likelihood. Now you say, I don't want everything in one cluster. I want to chop them, partition them in the other way. Then you recalculate those cluster center, you recalculate this mu and the sigma. Then what you do is, because everyone you get a maximum likelihood, then what you want to see is my new clustering versus the original one. Actually, the quality improves. Okay. If the quality improves, then I would assume this is better. The same thing as you want to merge them. You want to merge them into one. If the quality improves, you should merge. So that the hierarchical clustering algorithm general philosophy is you compute whether, from the likelihood point of view, whether merge or split give you better likelihood, give you better quality. If it's better quality, you do it. If it's not, you don't split, don't merge. So that's the general philosophy. Of course, what I should say is this kind of algorithm is mostly done in statistics community because the computation is much involved. many computer scientists, they like the algorithm more like a Birch, those kind of algorithms, because it's very scalable. Okay? And the computation is not as complicated as this. So that's a different flavor, different community. They prefer different algorithms. But clustering has hundreds of different algorithms and a different philosophy as well. So you can see the hierarchical clustering. That's a statistic point of view, and versus like a Birch or a Chameleon, they are more like computer science people. They want to do it in a way like constructed trees or doing the graph partitioning K and N, doing those games. So this different community. You cannot say which one is definitely a winner because the cluster is unsupervised in the sense, it's very hard even to judge which one is definitely the winner. Okay, so I finished in 5 minutes earlier. The reason is that we still need to do the course evaluation. I need 2 volunteers. One volunteer is distributing and collecting the evaluation sheet. Okay. Anybody in this class should evaluate because you are the backbone of this class. I think the other students not coming here so regularly, they either fully satisfied or unsatisfied the class, but they probably will not have a good chance to evaluate in this way. Okay, but they wanted a hard evaluation in this way. Only online students, they want you to do it online. Otherwise, they want to do it by hand. Another volunteer is distribute, because they said you use the blue ink, it doesn't count. It must be black and white. So they distribute the pencils. But our secretary complains the pencil quite often we distribute it, we cannot get it back. Okay, and then it wastes everybody's resource to cut woods to make more pencils. Okay, so we need 1 student to distribute the pencil and collect pencils. Another one distribute the sheets and collect it. Once you collect it, you can give it to the academic office. So I have to leave the room, so we need 2 people who will be volunteer to do this. You want to get this? Okay. And okay, you get a pencil? Okay, that's good. Okay. So you just enjoy the final rush and also the exam, okay? Thank you. I will be opening my office hours. I put in the piazza for the final week. The office hour, especially a few days before the final. And you are welcome to my office, especially the very last day. I will be in the office for the whole day. Okay, thank you.